Hello, welcome back to Larry's classroom. Today we're going to talk about current division by parallel conductances. Now, what does this mean? We're going to draw a circuit with some parallel conductances. We have some voltage source, voltage applied. We have some conductances. We're going to call this G1, G2, G3. And we have some total current going there. IT. I'm going to put negative, positive. We're going to assume IT flows that way. Negative, positive. We're talking about electron current flow. First, what is a conductance? Conductance which we represent by G, is equal to 1 over R, and the unit is Siemens. So if we had, say, a half ohm resistor, or say R equals 1/2, then G would be equal to 1 over 1/2, which would be equal to 2 Siemens. And then we put an S for Siemens, where the R is 1/2 ohm, the omega for ohms. Anyway, so we've got our formula for conductance. It's the reciprocal of resistance. And then we have a couple other formulas we're going to put up here. We have that I equals V over R, voltage divided by resistance, which you've seen that a number of times. Now, if we separate this formula out and say I is equal to, we'll say V over 1 times 1 over R, which is a valid way of separating this into two fractions. If we wanted to get back to where we started, we'd multiply across the numerator and denominator, we get V over R, just like we started with. Now notice this here, that 1 over R is equal to G, so we can do a substitution. We can say that I is equal to V over 1 times G. We'll put G over 1 just because we had a fraction here. And if we multiply across the numerator and denominator, we just get VG. So we have another formula of use to us here. I equals VG. We don't need this down here. Try to make that a little more legible. I equals VG. So current equals, I'm going to erase some of this extra stuff here too. But current can be calculated by taking the voltage times the conductance, or it can be calculated by taking the voltage and dividing it by the resistance. Now, for this circuit, remember the conductances in parallel add. So for this circuit, G total will be equal to G1 plus G2 plus G3, which is one of the reasons we utilize conductance rather than resistance. They add up so easily in a parallel circuit. Now IT using this I equals VG, we're going to go with V applied here let's just get rid of the A. We're only going to have one voltage in this demonstration here. Let's just call it V. So I equals V times GT. IT equals V times GT. So we can get the total current in this circuit by multiplying this voltage times the total conductance. Now if we wanted the current through any particular circuit, we could say that I through whatever branch would be equal to the voltage, which you see is, because of the parallel circuit, the voltage is the same here, here, and here. The V applied, or the V here, appears across every branch, exactly the same value. And we're going to use this thing, and we're going to say, just basically, for any branch, the current equals V times the conductance of that branch. So for this branch, it would be V times G1. For this branch, it would be V times G2. For this branch, it would be V times G3. Whichever one we wanted to find, we'd use the conductance of that. Now, let's do a substitution. Well, yeah. I'm not going to do substitution. We're going to multiply. We're going to take this formula. We're going to divide it by IT, and we're going to multiply it by IT. We divided this number by IT, and we multiplied by IT. We didn't change anything. If we take 10 and divide it by 5, it takes us to 2. Then we multiply the result by 5, it takes us back 10. So we did a division, we undid the division with a multiplication. But you'll notice that IT is equal to VGT. So we can do a substitution here. I equals VG over, we're going to replace IT in the denominator of this fraction with VGT. So, and we'll leave the IT over here exactly the same. So we have a formula that says I through any particular branch is equal to the voltage times the conductance of that branch divided by the voltage times the total conductance times IT. Well, we have a V voltage in the numerator and the denominator, so we can just cross that out, cancel those terms that are both appear in the numerator and denominator. We get a new formula. I equals G, the conductance of the branch, divided by GT, the total conductance, times IT. And this is what we will call our conductance voltage divider formula, which allows us, if we know IT and we know the conductances, we can easily calculate any of the branch currents. So I'm going to erase some of this stuff and move this guy up here. Get rid of that. We're going to copy this formula up here. So I for any branch is equal to the conductance of that branch divided by the total conductance times the total current, IT. And we're going to do a few examples. Well, I want this formula that GT equals G1 plus G2 plus G3. Yeah, let's put that somewhere else. It's not very good there. GT, the conductance total, equals G1 plus G2 plus G3 plus however many conductances you have in parallel. So we're going to do an example. We're going to erase this thing here. And we're going to create an example where we have two branches. And we're going to calculate the results of that. So here we got a two-branch circuit. So we got our R1, we'll give us some resistances. R1 equal to 4 ohms. And here we have R2 equal to 6 ohms. And we have IT we're going to call it, equal to 20 amps. So we want to do a current division calculation on this utilizing this conductance formula for current in each branch circuits. The current division formula using conductance. So first thing we need to do is convert these resistances to conductances. Well, we got the formula G equals 1 over R, so G1 equals 1 over R1, which equals R1 is 4, 1 over 4. So we're going to put 1 over 4 here for our conductance. G2, which will be conductance over here in the branch to the right, that's going to be using the same formula, but it's going to be this conductance formula here, the reciprocal resistance, 1 over R2, which equals 1 over 6. So we'll put that for our conductance right here. No, I didn't want to erase that conductance formula, so I'm going to put it back up here. I equals G over GT times IT. So we want to solve the currents through each branch utilizing the conductance formula. The conductance, the current division formula for conductance. So let's begin with that. I1, current here. I1. I'm going to put arrows that indicate this way. And we're going to put an arrow here for I2. So using the conductance formula, I1 will be equal to conductance 1, which is 1/4 over, we want GT times IT. Well, let's go ahead and just call this G1 right here. I1 will be G1, conductance 1, divided by conductance total times IT. Okay, here we just kind of copied that formula down, but we've put in some subscripts here. Now we have G1, we have IT, we need GT. So GT, remember our conductance was GT equals G1 plus G2 plus G3, however many we have. Well, we have two conductances here. So GT, the total conductance will be equal to G1 plus G2, which we have. What are G1 and G2? G1 is 1/4, 1/4 S. One-fourth of a Siemens plus G2 is 1/6 of a Siemens. Now, if we convert these to common denominators, we end up with 6/24 of a Siemens plus 4/24 Siemens, which adds up to 10/24 Siemens, which reduces to 5/12. So we have here GT, we'll put that right here, GT equals 5/12 and it's in Siemens. So now we have all the pieces. We have G1 right there, we have GT right there, we have IT right there. So let's make some substitutions to calculate this current I1. We'll say that I1 equals G1 1/4 over divided by 5/12, which is GT, and we'll put the S's here. 1/4 Siemens for G1. Let's put some symbols on here. I didn't put the S on here, so let's put them on there. 1/4 Siemens for G1, 5/12 Siemens for GT, and our current IT 20 amps. First, notice that we have a Siemens and Siemens in the numerator and denominator. Well, we can cancel units just like we can cancel like factors. So let's just get those out of here because they will cancel out. Now let's do some multiplication here. We multiply fractions by doing the invert the denominator and multiply. So it's 1/4 times 12 over 5. And that whole thing is going to be, that's 20 amps, times 20 amps. We have the inversion of the GT. Let's do a little cancellation. If we can cancel 4 out of both these, we get a 3. So we end up with, multiplying across the numerator, 3/5 times 20 amps. And let's put that over 1 and do some cancellation. Well, 20 can be expressed as 5 times 4, so we can cancel this and replace that with a 4, right? We cancel some like factors, we multiply that out. 3/4, 12, 1 on the denominator, we can just drop that because 1 as a denominator is implied, so we end up with 12 amps. So we have I1 equal to 12 amps. Now, there are two ways we can find I2. We can do the current summation formula, which basically says that IT equals I1 plus I2 plus I3 plus however many we might have. We only have 2 here, so let's do it that way first. IT, we have IT, well, let's do it over here. We have IT is equal to I1 plus I2. Now that we don't have any others, so I've dropped off the 3, 4, 5. IT is given to us, so we have 20 amps is equal to I1. We're going to substitute that in the 12 amps we just calculated. 12 amps. And plus I2, we do not yet know. But if we subtract the 12 from both sides, we end up with 8 amps equals I2. So we could write that over here, 8 amps. Give us a suitable answer for I2. Let's calculate I2 using the current divider formula. I'm going to erase this, give me a little room to work here. So, current divider formula, I'm just going to change this to a 2 because that makes it so to find the current through this right branch, I2, through conductance 2, G2, we've just taken this formula, put subscripts on it. This is IT, that doesn't change. IT, no, that's correct, that's I2. This is the one that's IT. So we took this I, we're solving for I2. GT doesn't change, IT doesn't change, but we're using conductance 2, G2. So let's see what we have. Do we have G2? We do have G2. Do we have GT? We do have GT. Do we have IT? We do have IT. Let's do some substitution, put them in there, and see what happens. So we'll say I2 is equal to G2, which is 1/4 Siemens. We're going to divide that by GT, 5/12 Siemens. And we're going to multiply that times IT, which is 20 amps. Again, we're going to cancel these like units from the numerator and denominator. The Siemens are going to go away. We just have a numerical ratio that we're interested in here. So take this down, I2. How do we do this? We invert the denominator and multiply. 1/4 times 12 over 5 times 20 amps. So we've converted our division. Remember, a fraction bar represents a division as well as a ratio. Kind of means the same thing. So now we've converted that into a multiplication. So we can solve this by multiplying the numerators, multiplying the denominators. But let's do some simplification first. 4 goes into 12 3 times. So if we replace that with a 3 and cross out the 4, we end up with 1 over 1 times 3 over 5 times 20 amps. That's I2. Well, the 1 over 1 times 1, we can just get that out of there that way, can't we? And we can put the 20 over 1 because every number has an implied denominator of 1. But notice that 20 is equal to 4 times 5. We'll put that up above there. Cancel that, replace the 20 with 4 times 5. But we now have a factor of 5 in both the numerator and denominator. We'll cross those both out. So now we multiply across the numerator and across the denominator. The amp stays here. That's 3 times 4 is 12. And the 1 on the bottom, we don't need to stick with that, 1 amp. What did I do? Oh, I see. I did the same problem again. Let's start over on that. I calculated I1 again when I should have been calculating I2. All right, I2. That's why I got the same answer I already had. 12 amps. I2 equals G2 over GT. So you got to see how to calculate a double job on I2 times IT. We do our substitution. G2 1/6 Siemens over GT 5/12 Siemens times IT 20 amps. Okay, let's see if that works a little better. Let's cancel the units like we've been doing here. Let's rewrite this as 1/6 times 12/5 times 20 amps. Now, we know that 12 is 2 times 6. We have a 6 here. So let's cancel that factor 6 in the 12. So it leaves us with 2 here and a 1 there. Well, 1 times 1, that goes away too. So our result is going to be 2/5 times 20, and let's put that over 1. Well, we see that 5 goes into 24 times, so 20 can be written as 4 times 5. So we're going to rewrite this as, we're going to cancel these 5, so we end up with 2 over 1 times 4 over 1 amps, which equals 2 times 4, 8 amps. And the 1, we don't need that anymore because that's the only denominator we have. So we got 8 amps both ways. So the current division by parallel conductance gave us the same answer as we got by utilizing the current summation formula for the second piece. And if you remember, this is the same problem that we did in our last lesson, and we got the same answers. We did that one with the calculated voltage and what was the formula we used? That was in the last chapter, wasn't it? No. Oh, we used the current divider formula with resistances. We used, I'm going to erase some of this. We used the formula that said I1 was equal to R2 over R1 plus R2 times IT. So when we did this before, I'll quickly maybe do one of them. We did the current I1 would be R2. Let's go ahead and do that one real quick. I1 equals R2, 6 ohms, over R1 plus R2, 4 ohms plus 6 ohms, times the same IT, times 20 amps. Now the currents can cancel. This becomes 6 over 10 times 20 ohms, and we do this cancellation here. That becomes 2. The numerator of this one goes away. This becomes 2. And we ended up with 12 amps that way too. So we did the current divider with parallel resistances, or the current divider with parallel conductances, we get the same result. And it isn't such a big deal with 2, but when you get a whole bunch of them, 6 or 8 branches, it's a lot easier to calculate with using the current division by parallel conductances. So we're going to do one more here. This guy's going to have, I think we're going to do one more here. Yeah, we got 3 branches here. Three parallel branches. R1 equals 10 ohms. R2 equals 5 ohms. R3 equals 2 ohms. Now we're going to calculate our conductances. Well, G1 equals 1 over 10 ohms, which equals 0.1 Siemens. G2 equals 1 over 5 ohms, which equals 0.5 Siemens. G3 equals 1 over 2. Oh, that's not right. 1 over 5 ohms was 0.2 Siemens. G3 equals 1 over 2 ohms equals 0.5 Siemens. So we took the reciprocal of each of these resistances to get our conductances. G1, conductance 1, was the 1 over 10. The reciprocal of 10, it was 0.1, 1/10. G2 was the reciprocal of the 5 ohms, 1 over 5. I'm going to make that a little bit more easier to read. R2 equals 5 ohms, and G2 equals the reciprocal of the 5, which was 0.2 Siemens, and R3 was the reciprocal of the 2 ohms, so it's 1 over 2, so G3 equals 0.5 Siemens. So we calculated the conductance of each branch, and we got 100 milliamps. We got IT equals 100 milliamps here. So let's utilize our current divider formula by parallel conductances, and let's find these currents, each of these currents. We'll find I1, we'll find I2, we'll find I3. Now, each of these currents, we need GT to utilize that formula. So we'll find out what GT is. GT, sum of all these, G1, G2 plus G3, well, G1 is 0.1 Siemens. Plus G2, 0.2 Siemens. Plus G3, 0.5 Siemens. We add this up, 0.15 plus 0.25, 0.4. No. Did I calculate this wrong? Oh, this is... Okay, this is 0.2. Okay. I'm reading these the S's like they're numbers. So I'm going to try to get them over here a little further. S. 0.1 plus 0.2 is 0.3 plus 0.5. That equals 0.8 Siemens. So we added this 0.1 plus this 0.2 gives 0.3 plus this 0.5 gives 0.8 Siemens for G total. So we needed that to use this formula. That's why we did this. So let's do I1. I1 equals, we're going to use G1, use this here formula here, the current divider formula by parallel conductances. So we're going to do G1 over GT, which is calculated 0.8. And I'm not going to put the unit Siemens on there because they're just going to cancel out. Well, let's finish. G1 over GT equals, times IT. Okay, there we put the proper subscripts for what we want to calculate. So now we're going to put G1 in there. 0.1. I'm going to leave the Siemens off because it's going to cancel. Over 0.8 times 100 milliamps. Well, 0.1 over 0.18, that is equal to, we end up with 12.5 milliamps. Let's write that down here. Equals 12.5. Let's do I2, the same token, same way. I2 equals, and we're going to go with, it's going to be G2 over GT. The only thing changes is we're going to be using different conductance. The conductance of the branch we're calculating the current in, which G2, 0.2 Siemens. And I'm going to have a Siemens on top and bottom, I'm just not going to put it in there. They'll cancel out those units. 0.2 over GT, 0.8, times IT, which is 100 milliamps. And this 0.2, you can see that's 1/4. 1/4 times 100 milliamps gives 25 milliamps. So let's write that down here for I2. 25 milliamps. And now we're going to do I3, which we're going to work it out pretty much the same way. I3, we're going to use that formula, only this time we're going to put G3 in there. The conductance of the branch we're calculating the current in. And we're going to divide that by GT, and we're going to multiply it by IT. So now we're going to put the values in there. G3, 0.5 Siemens. I'll go ahead and put the Siemens on here this time. They're just going to cancel, but GT, 0.8 Siemens. times IT, which was 100 milliamps. Now we'll cancel the units here. We'll just erase this Siemens unit in the numerator and the denominator. And we work this out. This comes to be, if you punch that into your calculator, 5 divided by 8 times 100, you get 62.5 milliamps. So we calculate each current through each of these branches utilizing the parallel conductance, the current division by parallel conductance. And if you add these up, 12.5, 62.5, that becomes 75 plus 25. You end up with 100 milliamps, just like we started with. So you see that this actually does work like we had hoped. So we kind of went through current division by parallel conductance. So we found we could do each branch by taking the conductance of that branch divided by the total conductance, multiplying it times the total current, and that would show us the current in a given branch. Now we're going to look a little bit at a series voltage divider with some load to it. And what do I mean by that? Well, we'll start with a little circuit, 120 volts, plus and minus, and we're gonna apply this to two series resistors to form a voltage divider. Let's make this a little nicer. And the upper one we're going to call R1, and that's equal to 80 k ohms. R2 is equal to 40 k ohms. We're going to label some points for reference here. Call this A, point B, point C. So we're going to do little calculations. We're going to figure out what our voltage is across R2 and the voltage across R1. Now, we remember our series voltage divider formula. Basically, the voltage was equal to R over RT times the voltage applied. And we're going to call this VA. We found the total resistance. We put the one we're trying to find the voltage across in the numerator, divide it by the total resistance, multiplied that ratio, that fraction, times the applied voltage. So let's work this out for each of these. Let's find V1. So we'll say that V1 equals, substitute this formula, R1 divided by RT times VA. Now we have R1, we have VA, we need RT. Let's do RT over here. RT is equal to R1 plus R2 plus R3. Well, what do we got? We got two resistors, so we'll just get rid of this part. RT equals R1 plus R2, so it's 80 k ohms plus 40 k ohms, which equals 80 and 40 is 120. So we have 120 k ohms for RT. Now we have all the pieces. We have R1, we have RT, we have voltage applied. So let's substitute that all in here. V1 equals R1, which is 80 k ohms, over RT, which is 120 k ohms, times VA, which is 120 volts. Now the k ohms cancel, and you do all the 120s will cancel too. You'll end up with 80 volts here if we work this out you could take your calculator and you could 80 divided by 120 times 120 and you would have 80 volts. So let's do the same thing with V2. We could do it two ways. We could know that the V1, V2 are going to add to 120 volts. Well, we would need 40 volts added to this to get 120 volts. I think you can probably see that. But we'll do the voltage divider method. Let's write this up here too. Let's write 80 volts here for V1. Let's find V2. V2 will be R2 over RT times VA, and a lot of the same players. The only thing changes here for this one is R2, which R2 was the 40k ohms. 40k ohms. And RT doesn't change, 120k ohms. And we're going to multiply that times VA, that didn't change either, 120 volts. Again, the units will cancel. 40 divided by 120, well, the 120s cancel. We end up with 40 volts, which is the same thing we just surmised by looking at the addition, how they would add up. So we've calculated this. Now let's think about what happens when we add a load to this. I'm going to erase everything but this formula here. So we're going to add a load to this. And I'm also going to 80 volts. Maybe help you see where the voltage is a little better. 40 volts. 40 volts across R2, 80 volts across R1. We're going to add a load to this. We're going to add another 40k ohm resistor. This is going to change the values, isn't it? The R equivalent down here, well, that's going to be utilizing the parallel branches of equal size. 40 divided by 2 is going to be, right there they are. It's going to be 20k ohms. So let's redraw this circuit with the equivalent. We're going to call this our load, by the way. That's the load we applied to our voltage divider circuit. We're going to redraw this real quick. 120 volts, 80k ohms. This is R1, and we're going to call this RE for our equivalent after we added the load of 20k ohms, because that was these two 40s in parallel divided by 2. So let's do the same calculations. New RT now. So let's erase this RT. We got a new RT now. RT now equals 80 plus 20. It's 100k ohms, right? We don't need to, we can add that up in our head, I think. So let's calculate V1. See, I'm sure it will change because we've changed the current by making that a smaller resistor. We're going to increase the current, aren't we? Which should make V1 to be a higher value than it was, because we have more current. By, yeah. So let's go ahead and do this. V1 equals R1 over RT times V applied. We do our substitution. R1 80k ohms. Now we have a different RT, which is 100k ohms, times the 120 volts applied. We punch this through our calculator. We end up with 0.8 times 120. What did we get there, Zach? Yeah, this equals 0.8 times 120 which is going to be, it's going to be 96 volts, I believe. Double check. Yeah, you have it with 96 volts. And you notice, as we predicted, R1 became greater because of increased current. Now let's do the same thing for let's call this, let's just call it VE because it's across the equivalent resistance. So VE will be equal to, instead of R1, it's going to be RE, which was the parallel combination of RL and R2, which we found to be 20 k ohms, over RT. That doesn't, well, it's a new RT, but still calling it RT because we calculated a new RT for our second problem, times still 120 volts. Let's substitute in our values. RE was 20 k ohms. RT was 100 k ohms times the 120 volts. Applied voltage didn't change from the first problem. But we have here now basically this 20 over 100 reduces to 0.2. 0.2 times 120 gives us 24 volts. So let's write these values on here. Let's say V1 was now 96 volts and VE was 24 volts. Which still adds to 120, but you see by loading the output, if we call this section here is the output of our voltage divider, by loading it with an additional power consumer out there, we drug the voltage down. We have less voltage out. Prior to this, we had 40 volts out, and now we have 24 volts out. So when we added a load, we increased the current, and that caused the voltage drop across R1 to increase. The value of this resistor, equivalent resistor value, was less. That caused the current through across the equivalent resistor to decrease by more than the current increased through that parallel combination. But here we've added two resistors of equal value. That's a pretty heavy load. Let's think about what would happen if we had a larger resistor on there rather than the 40 k ohms. Let's put a 400 k ohm, 10 times the value. Now that should not reduce this resistance as much, should not increase the current as much, should not increase the voltage drop across R1 as much, so our voltage out should remain a little higher. Will still go down from the 40 volts, but will not be as low as the 24 volts that the heavy load created. So let's erase some of these. We're going to recap. Okay, yeah, we don't. Let's leave that 40 volt here. That's the original problem. So let's change things around here. We're going to modify this circuit. These voltages are going to be different. This resistance, equivalent resistance, is going to be different. That's the biggest thing that's going to change the way this works. So let's figure out the equivalent resistance of R2 and RL. So basically, the two parallel resistors, I'm going to call it VE, RE, is going to be R2 times RL. This is the formula. You've seen this for two parallel resistors, R2 plus RL. Basically, the equivalent resistance is the product of the two resistors divided by the sum of the two resistors. What's that come to? R2 times RL is 4 times 40. Well, it's just 40 ohms times 400 ohms. And that's going to be over 440 ohms, because 40, well, let's write it in here. 40 ohms plus 400, well, these are all K ohms, excuse me, K ohms. And that's, what do we get when we do that? Well, 40 times 4 was 16000 over 440. And that all works out to, well, this is ohms, and this is ohms squared now. So we have, no, this is ohms squared. The numerator is ohms squared. Ohms squared and ohms, because we had ohms times ohms, we have ohms squared. We have ohms plus ohms, or K ohms. So we only can cancel one unit. So it comes down to 37 point, no, that ain't right. What was my 36.4 K ohms. And this is rounded a little bit, but it's 36.4 K ohms. So let's write that over here. 36.4 K ohms. So we have a different resistance ratio, don't we? Now let's do some voltage divider calculations and figure out what the voltage, we'll call VE, across the equivalent resistance. VE will be equal to R equivalent divided by R total times voltage applied. So, what is our resistance total after we did this new thing? RT equals 80 K ohms plus 36.4 K ohms. That is 116.4 K ohms, right? 116.4 K ohms. And I did round this a little bit, but I rounded to the first decimal place, what I did. So now let's do some substitution into this guy. RE, 36.4 K ohms. Over RT, 116.4 K ohms. And the VA, the voltage applied, did not change, 120 volts. The K ohms cancel. If you do all the calculation, 36.4 divided by 116.4, you end up, and rounding this to one decimal place, you end up with 37.5 volts. So let's put that on here, 37.5 volts. And let's look at what R1 would be equal to. We got 120 volts, 120 volts minus 37.5. That is 82.5, isn't it? Three. Yeah. So we end up with 82.5 volts here. So what do we observe here? Well, by having a larger resistor, our current didn't go up as much. We did find that this increased, but it increased to 80 volts instead of, what do we have for to 96 volts, before it increased to 96. So this voltage didn't increase as much as it did when we load it with the 40 k ohm resistor. And this voltage here did not decrease as much as when we loaded it with the 40 k ohm resistor. Now let's take a look at the percentage changes here. When we first, from the first change, we originally had 80 volts. And so to find out percent decrease, we basically did the output voltage, 40 volts minus, our output was 40 volts the first time around, minus 24 volts over the original 40 volts, and we multiply that times 100 to get percent. So 40 minus 24 divided by 4, it ends up being 6.25%. So our first, percent, not ohms. So we loaded it pretty heavily. No, that's not the right one. It ended up being 40%. 40% reduction. Basically 16 volts change was 40% of 40 volts. So our first, when we loaded the thing with we loaded this voltage divider circuit with a 40 k ohm load, which was a pretty heavy load for it, we had a 40% reduction in voltage. Now the second time, our original voltage was, unloaded was 40 volts. But we calculated with the larger resistor, the lighter current load, we calculated 37.5 volts, 37.5 volts, and still had the 40 volts originally times 100. And when we worked that out, we ended up with 6. If we subtract this and do the division and then multiply by 100, we end up with 6.25%. Which this is a little more than 6 times. When we loaded it with the 40 k ohm, we reduced the voltage by a little more than 6 times as much as when we loaded it with a 400 k ohm. So the 6.25 isn't perfect either, but kind of the moral of the story here is design your voltage divider so that this resistance is 1/10 or so of what you're typically going to put across the output. That way, and you may even want to go 1/20. You have a lot of current, what they call bleeder current through here, which is your static current. Well, it isn't. Your bleeder current is the total current, which you see the bleeder current increases when you add a load. And if there's a large difference, if this is 10 times or more resistance compared to R2, it doesn't change the resistance of the overall circuit as much. We have a more stable output voltage. So it's not a good idea to design a voltage divider circuit where this resistor is really small in comparison to the output load. Now, a lot of times you're using these things to provide a voltage level to a high impedance amplifier that draws very little current. So these voltages don't change very much when you hook this amplifier up to them. But the greater this value RL is compared to R2, the less change in voltage you'll have when you add this load. Anyway, thanks for coming back. I appreciate your like and subscribe. And until the next time, keep on learning.